Hey everyone, welcome back, and today let's solve Leetcode problem 1726 titled Tuple with same product. So we're given an array nums of distinct positive integers. Distinct is very important in the case of this problem, and we need to simply return the number of tuples containing four elements A, B, C, and D, such that the product of A and B equals the product of the other two elements C and D in that tuple of length 4. And all four elements A, B, C, and D have to not only be elements of nums, but they also all have to be distinct. Now, in the case or context of this problem, we're already given that all the integers are distinct. So what that really means is that basically we want to find all of the elements A, B, C, and D such that they follow this property of multiplication, such that their indices are different, right? Because we know that their values are obviously going to be different because each value is distinct. We just wanted to choose four different elements from different indices or distinct positions in the array that follow this A times B equals C times D property. So in example 1, we have our input array nums to be 2, 3, 4, 6. And in this case, we have exactly 8 different possibilities, or 8 valid tuples. In this case, that would be 2, 6, 3, 4, 3, 4, 2, 6, 2, 6, 4, 3, 4, 3, 2, 6, 6, 2, 3, 4, 3, 4, 6, 2, 6, 2, 4, 3, 4, 3, 6, 2. Now with these values, there's something very, very important to really notice here. We're basically just rearranging the elements in this combination that we chose, right? A, B, C, and D are 6, 2, 4, and 3 in no particular order. We're keeping all the elements for this for all these valid tuples. We're just rearranging them while actually keeping the same exact answer as such, right? Because as you can see, 2, 6, 3, and 4, those are all the common elements in all 8 of these tuples. It's just the ordering that differs, but even then, we still guarantee that they all follow the property of having A times B equals C times D for the 4 elements in the ordering of these all tuples, and they are all valid. So in this case, we have an output of 8. More on that later, but just kind of want to introduce how that kind of pattern works. In example 2, we see that we have 16. In this case, basically, one way to think about it is 8 times 2. There's 2 different rearrangements of 8 tuple combinations of 4 elements at a time. And to better elaborate, we see that the reason why there's 16 valid tuples, first we have 1, 10, 2, 5, 1, 10, 5, 2, 10, 1, 2, 5, 10, 1, 5, 2, 2, 5, 1, 10, 2, 5, 10, 1, 5, 2, 1, 10, 5, 2, 10, 1. Those are all the unique rearrangements using these 4 elements, A, B, and C, and D, to meet these criteria. Great. Next, the other rearranging of 8 tuples, or 8 different combinations of elements, would then be 2, 10, 4, and 5, 2, 10, 5, and 4, and so on and so forth. Right, notice how all of these elements in the bottom 2 rows would all be using the same exact elements in a different rearrangement, and same logic applies for the top 2 rows. Very important to note for this problem. And we have 8 of each different combination of each different quadrat, I should say, of 4 unique values. So for the constraints here, we see that the length of our input array nums is not going to exceed 1000, which is relatively small, at least for runtime and memory complexity. And we're also given that any value at index I in the input array nums is not going to exceed 10 to the 4th power, which is also relatively small. I wouldn't say relatively small, it's pretty average of a constraint. And we're also given that all the elements in nums are distinct, which is pretty helpful and pretty key to know to solve this problem. So how can we kind of lead to our solution here? What is a good way to kind of lead to our solution? Before I get more into that, I will give you guys a few seconds to kind of just think through this problem and kind of explore the constraints. And then in a few seconds, I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so like we usually start, how can we kind of make observations to help us lead to the most efficient of solutions? Well, the first observation, and honestly the most important that we should really make, is that multiplication is a commutative property. And to better explain this, let me actually comment this out. Multiplication, I think this is how you spell it, correct me if I'm wrong, commutative. The multiplication is a commutative property. This should be it. Commutative, yeah. It is a commutative property or a commutative operation. Now, what that really means is that the order that we multiply elements in, they don't matter. It's just the elements that we actually multiply, right? The product is going to be the same for the output regardless of the rearranging or the arrangement of the elements. So to better put that into example here, if we had 5 times 3, this would still be equal to 3 times 5, or even, sorry, and even if we had something like 4 times 7, this would still be equal to 7 times 4. The same thing applies with 3 times 9 and 9 times 3, or 7 times 1 and 1 times 7. It's always going to be the same exact product or the same exact output, regardless of the arrangement that we actually arrange the elements in and multiply them, as long as the elements themselves are the same. And for context and just for general knowledge for future problems, the two operations, or rather the main operations that are commutative, would be addition and multiplication. For example, 5 plus 3 is equal to 3 plus 5, 10 plus 9 is equal to 9 plus 19. The order that we add or multiply does not matter, hence the reason why they're called commutative. And subtraction and division are actually not commutative. I'll just say non-commutative. And very simple proof here, we'll just simulate that. If we had something like 5 and 3, 5 divided by 3 is not at all equal to 3 divided by 5. Those are two very different things. And of course, in terms of subtraction, 3 minus 6 is definitely not equal to 6 minus 3. One is negative, the other is positive. Very important to note. So applying that kind of logic here with multiplication being a commutative property, how can we actually apply that in the context of this problem? Well, very simple here, right? Let's say, I'll just kind of comment this out. We know in our solution here, if the pair A comma B, if that is a valid pair, so if AB is a valid pair, we know for a fact that BA would also be a valid pair. We're just literally rearranging the elements A and B to B and A. Of course, the product between these two elements would obviously still be the same, regardless of the arrangement that we multiply them in, because multiplication is actually commutative. And applying that same exact logic for the C and D parameters, so that basically means if C and D is a valid pair, logically, the same can be said with their opposite, which would mean D and C is also a valid pair. These two pairs or arrangements of elements are interchangeable because DC and CD both have the same exact product. Similarly, AB and BA both have the same product. Multiplication is commutative. The order in which we multiply elements does not matter as long as the elements are the same. They are actually interchangeable. Now, this is where we actually get or lead into the most important part and the biggest optimization of our solution. And that really is applying this logic that multiplication is commutative. We don't even need to count all the duplicate pairs or arrangements of A, B, C, and D values separately, because going back to our examples, the moment we found a pair, or rather 4 values that met this criteria, we immediately realized that there would simply just be 8 different rearrangements of those 4 values still meeting that criteria. 8 different rearrangements as long as 4 values meet this criteria of A times B equals C times D, right? Because of course, to kind of list them out here and to better dive in why that really is, again, since AB, assuming we find a pair AB and another pair CD, right? In that case, A times B, for the context of that problem, A times B would be equal to C times D, exactly how the problem tells us that. Now, assuming that, we know we can form exactly 8 different tuples of rearrangements with these 4 values here, applying or meeting this criteria, because to kind of simulate this, the order of AB and CD can be swapped. That means AB is equal to BA, and CD can also be interchangeably equal to BA, or rather DC. Now, within each of those unique pairs, the individual elements can also be swapped, meaning we can have AB and CD, we can have DC and BA, and so on and so forth. And that would give us exactly 2 times 2 times 2, or 2 to the power of 3 permutations, which is a result of 8 permutations. And I know a lot of people are actually visual learners, and so to kind of demonstrate this, how this would actually look, again, assume, as we actually iterate through the array, if per se the 4 elements A, B, C, and D, if they are actually a valid tuple, so let's just say if the tuple with A, B, C, and D, if it is actually a valid tuple, if that is a valid tuple, where A times B is equal to C times D, then the 8 unique or different permutations that we can make would be A, B, C, D. That's the first one, of course, the most logical one. We could also make, give me a minute, guys. We can also make A, B, D, C. That would also be completely fine. I don't know why my cursor's not working. We could also make B, A, C, D. Hopefully this is formatted correctly. Sorry about that, guys. And after BACD, very similarly, we could also make BADC. So let me add that on. Yeah, it's a very bad formatting for me. Sorry about that, guys. And then we could also make for their fifth permutation CDAB. This is where the CD pair actually comes in first. We could also make CDAB. And literally just reversing these two elements, we can also then, of course, make CDBA. And finally, for the last pair of permutations, we can have DCAB, and you guessed it, DCBA. Notice how this forms a very, very simple pattern. If, again, to reiterate, if A, B, C, D, those four elements, if they are a valid tuple, meaning A times B is equal to C times D, those products match out, then of course we're guaranteed to have exactly 8 different permutations that are still valid with rearranging those 4 elements. We could have these guys. I'm not going to read them out. That would take longer than needed, and so that's something very important to know. Now, how can we actually form these 8 tuples? Let's actually break down how that works. Again, each pair can be written in 2 ways. What are those 2 ways? Either A, B, or they can be written as B, A, right? And very similarly, applying the same logic for the second pair, C, D, or we can have D, C, right? That is kind of the commutative property of multiplication. And applying just these 2 splits or permutations, we get 2 times 2 permutations, or rather I should say combinations. So 4 combinations, just swapping them. But individually, within each individual tuple, we can also split the order of the 2 elements in each pair, right? The entire tuple A, B, C, D can also be reordered by simply swapping the first pair with the second pair, and so on and so forth. And effectively, we can basically double the number of rearrangements that way to get a total number of rearrangements to be 4 doubled, or basically 4 times 2, to be equal to 8. That is 8 total unique ways for every single unique tuple of length 4, basically A, B, C, and D parameters or values that meet the criteria of having the same product, meaning AB is equal to CD. Those 2 products are the same, and that's basically how that would work. Okay, now with that high level, or rather I should say very lengthy explanation, let's go ahead and talk about how we can actually implement that method, or that commutative property, into our solution. Effectively, again, to kind of reiterate how we're actually going to do this. Again, basically we're going to iterate over all the pairs. Let's just, to avoid confusion, I comma j in the array, and then for every pair ij, would simply compute their product. And simultaneously, in each iteration of this ij nested loops, we're going to store these products of ij after we compute them in a hash map, which is in Python simply just a dictionary. And in that dictionary, the key is going to be the product of each 2 elements. And of course, the value is basically its counter, or its frequency. And to better elaborate, formally, its key value pair would be the count of how many times we have already formed or seen that product before with 2 other elements, I, j, in each iteration of the array. Right, and of course now, if a product does actually appear more than once, meaning its frequency is greater than 1, that means there exists multiple tuples or solutions that actually satisfy our condition of having AB equal to CD. And for each product per se appearing k times, well then the number of valid tuples would be actually given by something called the combinatorial formula. I'm actually going to type that out as well. Combinatorial, I hope that's how you spell it, formula. And what that formula is, to kind of reiterate, for every single product of two elements ij that appears k times, the number of valid tuples of those elements would simply be given by the combinatorial formula. And that would basically be where the valid tuples for those parameters or values a, b, c, and d would simply be 8, like we talked about before, of those different rearrangements, times k minus 1, and this entire thing is going to be divided by 2. Now, I'm not going to sit here and devise this math formula. I would assume it's somewhat complex, at least for the context of this problem. But to kind of explain, this is basically the formula that gives us the number of valid tuples for each product that appears k times. That's why we have k in this formula here. And the reason why we actually multiply by 8, to kind of go back to our previous explanation, each valid pair a, b, and c, d, forms 8 different permutations, right? Each a, b, c, d length 4 tuple would have eight different permutations to form, meaning that AB equals CD, 2 pair equal product criteria, right? Now, of course, for the data structures that we're going to be using, for the memory that we're going to be using, we're going to use the dictionary or a product count, basically storing every single unique product that we see as the key, and its key value pair basically is going to be mapped to the number of occurrences, basically the number of times we see that product, and of course, we're going to have another variable result that's simply going to store our return value. It's going to be the number of valid tuples, its final count that we actually see in the input. So with that very long explanation, sorry about that, guys, let's go ahead and get straight into the code here. So what I'm first actually going to do, like I just talked about, I'm going to initialize my product count hash map. Now I call this product count because it literally maps every single product that we form with two elements in each iteration of the input with its corresponding frequency, meaning the number of times we see that specific product. Now in this case, because Python is a very flexible and easy to use language, I'm actually going to be using something called the default dict. This is also known as the default dictionary. That's why its short form is the default dict, right? And in this case, for my immediate or default key value pair, I'm going to be taking an integer, right? Basically, again, it's going to store the product frequencies, and every single key, its data type is going to be in the form of an int, or long form, an integer, right? And now once we actually initialize this product count, let's actually get the result. This is going to be our return variable, and as you may imagine, it's simply going to store the total number of valid tuples. It's going to store basically our final answer, right? Now, you don't have to do this. This is kind of optional. This is just going to help me iterate through the array later on. I'm going to store n and grab that as the length or the number of elements in our input array nums, right? This really just is basically avoiding us to call length of nums repeatedly, just an easier way to actually iterate through the array. Not really necessary. If you guys don't want to do it, feel free to just not do it and simply iterate regularly. Up to you guys entirely. And I don't think it's the most effective of things to do in languages other than Python, right? So now let's actually iterate through all the pairs I, j in the input and check with their corresponding product frequencies and resulting combinations 8 times. So for I in the range of the length of the input array nums, basically in this case n, and the nested loop is going to be for j in the range of, to get all the unique pairs of elements, I plus 1 from that element, the next element, up until n. Right? Here we're literally just getting all the unique pair of elements from unique indices as a pair in each iteration of this nested loop here. Right? We're going through all the unique pairs, and we're ensuring, starting from I plus 1, that j is greater than I. That is how we actually don't form any duplicate pairs or use the same index exactly twice, or reuse the same index. Now, in each iteration, we're going to store the product or get the product of the current two elements nums at ij to basically literally be the current element nums at I times the current element nums at index j in this iteration, whatever value nums or whatever value I and j is. We're simply calculating for each pair their product, right? And now, once we actually compute the product of the current pair of elements, nums at index I and index j, we'll actually increment our result with the number of arrangements that we can actually form, meeting that criteria, with the current product accordingly. And the way we can do that is simply increment our result variable, the integer, with 8. This is the formula that actually comes into play. 8 times the product count of the product. Now, product count of the product literally just gets the number of times that the product appears, right? That's why we're passing in the product as the key in this product count hash map. And the way this works, that's honestly the main part of this solution. Effectively, the key insight here is that every single time we actually find a product that already exists in the product count, that's also the whole reason why we use the default dictionary. Every time we actually find a product that already exists, we basically already have k times k minus 1 over 2 ways to actually form new valid tuples. And since we know that every single tuple A, B, C, D has to have and always will have exactly 8 different permutations, as we discussed right here, we know that we simply have to multiply that formula with 8, where that formula, again, is basically going to be the number of ways to form new valid tuples with a product that appears k times. And in this case, that k value is simply going to be product count at product, because that's the number of times that the current product appears with the current two elements nums at I and nums at j. Each repeated product will simply add 8 valid tuples to our result. And effectively, once we're done incrementing the result, we're simply going to increment or update our product count at the current hash map or at the current product and increment its frequency by 1. Because, of course, we've literally just seen it one more time. We've formed it again with 2 more unique elements in this specific iteration, and so we're basically going to increase the count of this product in this iteration or frequency in the dictionary by 1. And effectively, once this for loop is then executing, meaning once we've actually iterated through every single unique pair of elements in the input array from different indices, we simply want to return whatever our result is, because this, of course, is going to store the number, or rather total number, of valid tuples that we can actually form where AB is equal to CD with the same exact product, right? So unless I made any syntax errors here, this should be accepted and there should be a valid solution. So let's go ahead and double check that. And as you can see, this really is just about as efficient as you can really get it to be. So to kind of reiterate how the code actually works as a whole, effectively we're simply using these nested loops to calculate every single unique pair of elements, nums at index I and j, and for every single iteration or pair of elements that's unique, we're going to calculate the product and store that in the dictionary. And whenever we see, and the key part is, whenever we actually see a product that we have seen before in the default dictionary, we simply count the number of valid tuples using that formula and multiplying that formula by 8. So 8 times k minus 1 over 2. And effectively, we're simply returning the total count as the number of valid tuples that we can actually form. The number of different rearrangements of parameters A, B, C, and D that did have the same product as a pair, right? And it is really just about as efficient as you can get in the context of this problem. And that gets us into what the runtime and memory or space complexity is. The runtime complexity is actually going to be a big O of n squared, because really we have nested loops, right? We have these nested loops going through every single pair or iterating through all the unique pairs. That would already be an n squared complexity. And of course, within each iteration of these nested loops, we do actually technically have other operations like dictionary operations, which would be like inserting and looking up. But of course, the cool thing about hash sets and hash dictionaries is that they are actually very efficient in lookup time. They are actually a big O of 1 or constant lookup and inserting time on average, and so they aren't actually going to affect our complexity, at least in a very significant manner. And so our overall fully simplified time complexity or runtime complexity is actually a big O of n squared. And for the memory or space complexity, we are actually using this extra dictionary product count. And the key thing about this is that it's not actually completely linear, because of course, again, we're using it to store the product counts with their corresponding frequencies. And in the worst case, we would actually store all n times n minus 1 over 2 products. And to kind of comment that out, worst case, this dictionary or this hash map would store all of the n times n minus 1 under the formula here, and this is all in parentheses. It would store all the n times n minus 1 over 2 products, and that would still be, because if you FOIL this out, this would be n squared minus n over 2, which really, just fully simplified, is a big O of n squared memory or space complexity, right? That would be the fully simplified space complexity. And so it is a big O of n squared, or a quadratic solution for both the runtime and space complexity for the solution of this problem. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.